questions on Piazza, such as do we have a class today, which I am answering in the affirmative. So if you have other questions, just put them there. So yes, we do have a class. So we'll go through the last section in the book. We will finish up the lab. I will say a few things about the lab, and then after that, to reward everyone who's been sticking around for all this time, I will give a few tantalizing hints for the final that will not be recorded, so as to reward those who are actually here. All right, that's the agenda. So let me get going, and then I'll come to questions later. Or does someone want to shout out a question? Yes. Okay, let's have a quick look at that. So, you know what? How about I lecture about that, and then when this comes up, then I'll segue into it. All right. So tree traversal. So you have a tree that was already built up by a bunch of inserts and maybe edited by a bunch of removes. So the tree is there, and now we want to visit all of the elements in the tree. So for a BST, the most natural way of doing traversal is what's called in-order traversal, where you have your tree here. The tree has a root. It has a left subtree and a right subtree, where you say, first, look at the left subtree, then look at the root, and finally look at the right subtree. And what does it mean to look at it? You know, to look at it is that you take off your glass and you stare it down. No, I mean, it depends on what it is that you want to do. Maybe you just want to print the elements in it. Then to look at it means you print it out. Maybe you want to compute the sum of all of the elements in the tree for whatever reason. Then you would take that element and add it to the sum. So really, when you look at something, it's the element in the root that is your focus. Because when you look at the left subtree, you recursively, again, have to look at its root and so on. All right, so in-order traversal means first the left subtree, then the root, then the right subtree. And because of the way that a binary search tree works, in a binary search tree, you know that everything to the left is less than the root, everything to the right is greater than the root. And that's true for all of the subtrees. So when you visit a binary search tree in order, then you see the elements in sorted order. And so if you wanted to print them, that might, for example, be a good property. Now that's not the only possible traversal. There are pre-order and post-order, and they just make minor modifications to this. So in pre-order, you first visit the root, then you visit the left subtree, and then you visit the right subtree. In post-order, you first visit the left subtree, then you visit the right subtree, and then finally you visit the root. So those are really the three ways of doing it if you have a binary tree. In a binary tree, you have the thing on the left, you have the root, you have the thing on the right. There's only three possible ways of ordering the visit. Now, pre-order and post-order actually make sense for trees with arbitrary numbers of children. So this tree here could have more children. And so pre-order simply means visit the root, then visit all the children. And post-order means visit all the children, and when you're all done, then you visit the root. For in-order, on the other hand, in-order only makes sense for a binary tree. Because it's visit the thing on the left, visit the thing on the right. If there's multiple things, it's not clear where you would schedule in the root. So pre-order and post-order work for arbitrary trees, in-order only for binary. So what's the use? Never mind what's the use. Let's first of all see that you can do this. So that'll be your last chance to get Piazza points. So let's see. So when we do in order, we first visit the thing on the left, then we do the middle, and then the right. Well, which surely must be that. So now I visit the thing on the left. So that one doesn't have anything on its left, so I don't do it. Then I have the root, and then I have this one. Actually, it has to be the letters in sorted order. So that rules out 2 and 4. Well, 2. Now let's do it in pre-order. So in pre-order, we do the F first, then we do the left tree here, and again in pre-order, so we do the root first, and then this guy. So that's good. And now in post-order, let's see, we do the F last, and then we do the left, and then the right, and for the left, we do the D last, and so this would be option 1. Let's see if we have, huh? Say again? All right, so I have to do it again. Sure. So pre-order is, okay, F comes first. Oh, I see, and then comes D. Yes, yes. All right, good. All right. So you're right and I was wrong. All right. I'm sorry? What was that? Okay, well, let's do it. So post order means F comes last, and then I visit this thing in post order, which is E and then D, because the root comes later, and then this one here. No, it's this is post order. Oh, yeah, you're right. It is number 4. Oh, great. All right. I mean, I only put in number 4 because just in case I messed up, but it looks like I'm getting to cash in my chips here. All right, so it's a fiddly thing to do, and just do it slowly one more time at home. There won't be any actual exam question with it, but maybe there should be. All right, so what's the use? I mean, it sounds like a weird thing to look at all of these traversal orders, but they actually have a few practical applications. And so here's one. Remember those expression trees that that we had before when you have an arithmetic expression? Am I asking? No. So the first expression here is what we would normally write as 3 plus 4 times 5. The second one is 3 plus 4 times 5, fully parentheses. And each of those correspond to a tree. And now when you write that tree out in post order, so if I look at the first tree here, this tree here becomes 3, 4 plus in post order. This one here is just 5. And then the star gets attached all the way at the end. The tree over here, I have, this one here gives me the 3. This one here gives me a 4, 5 star in post order. And then the plus comes in here. And when you do all of that, you get the reverse Polish notation of the expression. And now you might say, well, who cares? But people actually care when they write a compiler. In a compiler, one builds these trees. There's a process called parsing that results in these trees. And then when you read out those expression trees in post order, then you get exactly what you need to feed a stack-based processor, such as the Java Virtual Machine, which does take a reverse Polish notation for these things. So it's a practical application, at least for someone who writes a compiler. Here's another practical application. Suppose that you have a tree representation of all of the directories and files that you want to do some operation with. So here I have a directory called sample code with subdirectories chapter 1, chapter 2, section 4, and so on. And now my task is I want to delete all of those subdirectories, the directory and all of its children. Now, when you want to delete a directory, it must be empty. If you try to delete a directory that is not empty, the operating system is going to give you an error. So in this case here, you must delete first the leaves. Oops. And then after you've deleted the leaves, then you can go and delete the other levels and so on. And so if you traverse the tree in post order, that'll work out beautifully. Because in post order, you first visit all of the children before you visit any of the parents. So if you were to visit this big tree here in post order, the very last thing that would be visited would be the root directory. But before that, we're dealing with this subtree and this subtree. When looking at the left subtree, the last thing that's visited is this directory. The first thing is that directory. So this one will get deleted first, then this one will get deleted, and then it'll move on to the tree on the right. And so thereby, you can always schedule the delete operation. It'll always delete a directory that's, that has nothing in it. So post order is the right traversal order if you want to clear out a directory tree. Now look at a slightly different situation. Suppose you want to copy a directory tree. In this case, it turns out that pre-order is the ticket, because when you want to copy a tree, you have to first start copying the root, and then you can copy the left subtree, and then you can copy the right subtree, but you have to have copied the root first so that they have a home where they can be put in. So in this situation, if you want to write down all of the copy operations that are necessary, then pre-order is the ticket. So I just wanted to show that there are practical situations where these traversal orders do matter. All right. So here's another somewhat practical situation where I asked, suppose you have these two directory trees and you want to find out whether they contain the same subdirectories. Now this is actually a useful thing that you sometimes want to do. Like a student sends you a zip file and later another zip file, and you unzip them both. You want to know whether they're identical, or if not, where did they differ. So my question is, when you want to do something like that, which of these traversal orders do you need to choose? Yeah, that's interesting. So it can't be in order. Why not? A directory tree is not necessarily a binary tree. Right? In a directory tree, you can have any number of subdirectories at a given level. In order only works for binary trees. So so pre-order will surely work. You can visit them in pre-order, and you'd have to kind of visit both trees in some simultaneous way, and if they then if they match, you're good. Post-order will work the same. Will work just as well as long as you use post-order on both of them. So it doesn't strictly matter which of the two you do use. It all depends on, of course, what we really mean with having the tree. So my idea is that the tree has already been built in some way, and then you can just apply a pre-order or post-order operation to it. It's actually a little bit more subtle than that, because when you make it, and I think I'll come to that in the next slide, so let me just skip ahead with that. Because now we're getting down to the nitty-gritty. What does it really mean to visit? And so you call a method on the entire tree, and that method is going to somehow recursively call itself so that it ripples down to all of the nodes in the tree. And then you need to say what should happen at each of the nodes. And for that, you need to give some kind of an operation. So it's customary to have an interface for that, and we'll say that we'll supply some class that implements visit, and we give an object of that class that says how the visit should be done, and then the visit method gets called. So this method here gets called on each node. So you can think of a visitor as kind of maybe similar to a comparator, where when you sorted an array, different array elements were picked and were compared. And here a visitor, same kind of thing. The pre-order method gets applied to the tree, and then it in turn calls back the visitor on each node. And so it really depends on what it is that you want to do. If you wanted to print, then that would be very simple. You would simply call in your visitor, you would put a call to system.out.println. If you wanted to delete or copy files, well, then you would have to figure out what are the operating system's calls to make that happen. So here I have an example of a typical visitor. For whatever reason, I want to count all short names that are stored in a tree that contains strings. And so I've built up my tree. Here it's a binary search tree. It doesn't have to be. Any tree would work. Because, actually here I'm visiting in order, so I guess it did have to be a binary search tree. Here I have my visitor. So it's a class that implements the visitor interface. It has a visit method. When one visits an object, then it calls toString, gets the length of that string, and if that is at most 5, then we count that word as short, and then we increment a counter. Which counter? Well, it's an object, so it has an instance variable that's an integer, and that instance variable gets incremented. So to actually make the call, I have to make an instance of this visitor, which I call v, and then I pass v as a parameter to the call to bst.inOrder. That now calls the recursive helper, and ultimately in the recursive helper, we'll see that over here, except sadly with preorder, in the recursive helper, whenever we visit a node, then the data element gets passed on to the visitor. So it would then pop out here, and we would see its length. So in the end, I print the number of short names, and then how do I get the count? It's that instance variable in here. Since the class is a local class that's nested inside a method, it's okay to leave that instance variable public. So that's the procedure that you need to go through every time that you wanted to make a visit through a tree. You need to set up an object of you need to set up a class that implements the visitor interface, and whose visit method does the right thing, whatever that might be, printing the thing, or in this case, computing the length or whatever. And if you need some extra state, that's okay. It's an object, so you can put in whatever state you want. Now, back to that question on how could you reasonably use this technique to find out whether two trees are identical? Because that's not so easy. You would really, because you make one visit, and then afterwards you make the second visit. They're not really coordinated in any way. So the first visit would have to put all of the files that it finds in some collection, let's say in an array. And the second one would put all the files that it finds in another array, and then afterwards you could see whether they are the same files. That would be one way of doing it. All right. So when you do a visit, then that visit is going to go on for the entire tree. And so the intent is that you really want to see every single element. And that's often very appropriate if you want to harvest the entire information. But it's not what we typically have been doing with the Java APIs. In the Java APIs, we've not really said, let's apply this function to all of the elements. Instead, we've said, give me the first element, give me the second element, give me the third element, and then it was up to the code that received the elements to do something to it. So that approach is called iteration. And so iteration and visit are pretty much the same if you really want to see everything. If you want to see the entire tree, then it doesn't much matter whether you set it up with a visit or with an iterator. Iteration has an advantage if you only want to visit some number of elements, say until you have found the first one that makes you happy, or until you've seen 10 of them. So as an example, consider the data set that Google has about web pages. And now you make a search, and you want to see the results. You don't actually want a visitor to be applied to the results because there are 10 million of them. You probably just want to see the first 300 of them. So in this case, an iteration through the results that you can cancel is better. So that's the advantage of the iterator. And so how do you make an iteration protocol? One way that you could do it is you could make a visitor, and that's what the homework assignment, or one of the homework assignments is about. You could make a visitor that returns a Boolean so that it stops visiting. But if you think about it, it's still going to make a fair number of unnecessary visits. Let me explain that part. So let's say I have this tree, and my visitor says, I want to stop visiting after the fourth element, say. Then, let me make this one. Yeah. So in this case here, we would visit this guy, would visit this guy, we would visit this guy, and we would visit this guy. And at this point, the recursive call still goes back to this call, which then returns false, to this call, which then returns false, and then to this call, which then returns false. So there's a few levels of nesting that you have to unwind yourself out of. And so let's say we want to avoid